So we're going to finish up by talking about what happens when we have two different wave sources. And there's a concept that we need to become familiar with, which has to do with waves traveling different distances towards their destination. So for example, what if one wave has completed 2 full cycles by the time it gets to a point, and this other wave has only completed 1 cycle by the time it gets to a point? Well, this is actually fine because at the moment that they meet, they both have a maximum. So we can say that these waves interfere constructively. Now, what happens if one wave has completed 1 cycle and one wave has completed 1.5 cycles? Well, now we have a little bit of a problem because when one wave is arriving at a maximum, the other wave is arriving at a minimum, and they're going to cancel out. So we say that these waves are interfering destructively. And the point that I have to make here is to do with something called the path difference. And in order to apply these formulas, we have to assign our point to some kind of number. So if we come over to the right hand side here, this is a clip from Veritasium, the YouTube channel, and Derek has set up this experiment where he's bobbing 2 balls up and down at exactly the same time. And what's happening, he's got points where the waves are interfering constructively, which is in purple, and they are the antinodes. And he's got points where the waves are cancelling out and the water is completely flat, and that's in orange, and they are the nodes. Now I'm going to start labeling with this being 0, and then our first node is a 1, our first antinode is a 1, 2, 2, and the same thing on the left. If the waves are arriving in phase and creating an antinode, we can say the path difference is n lambda, where n is just the number up here, or the order of the node or antinode, if you like. What does that actually mean? Well, like in our first example, the difference in the distance that our waves have traveled is 1 wavelength. But it could be a difference of 2 or 3, as long as it's an integer. So n must be an integer for this to work. On the other hand, if we're looking at a node in orange, a path difference is n minus a half lambda. So for example over here, this would correspond to the first node because the difference is half a wavelength. If we put in n equals 1 over here, we get a path difference of half a wavelength. So if we come over here now to our speaker example, maybe you're listening to, I don't know, Billie Eilish or something, whatever everyone's listening to these days. Gee, this'll age well. Let's put a point down over here, and let's say you're standing there. And a common exam question might be, if we know that it's 20 meters from one speaker, and we know that we're standing at a point where it's quiet, in other words, we'll be standing at a node, then how far away are you from the speaker on the right? And they might give you some data, like the wavelength that you're listening to is 0.8 meters. And let's just pretend that this is the order number 1. It's the first node from the middle. By the way, if you just started walking in a straight line from left to right, you would notice periods where the sound is quiet and periods where the sound is loud for exactly the same reason. But I digress. So let's say this is the first quiet spot from the middle. We can use the path difference is 1 minus a half times 0.8, which would be 0.4 meters. And on the left-hand side, we can just write this as 20 minus S2. I'll call S2 the distance from speaker 2. So 20 minus S2 is 0.4. We can do some simple algebra here and say that S2 is 19.6 meters away.